Okay, so now that we've talked about position and displacement, it's time to talk about things moving. All right, so motion. And to get ourselves started with motion, we're going to actually look at some graphs. Okay, graphs are going to be an important tool for us throughout the year. And so let's first talk about what kind of graphs these are. So these graphs are telling the story of two different armadillos. Okay, and I don't know if you've seen an armadillo before. I've seen a few, unfortunately. When I used to live in Texas. I lived there for 2 years and taught there. Unfortunately, the only ones I saw there were former armadillos on the side of the road. So never was able to see one that was live, but they're interesting creatures to say the least. So anyway, we have two armadillos, and we've kind of graphed their motion in some position graphs. Okay, and so these are graphs comparing the position on this vertical axis and time on this horizontal axis. So this is going to be maybe something you're not very used to, having the x be the vertical axis, but often in a position time graph we'll have x vertical and time horizontal. Okay, and we're measuring position in meters, time in seconds. Okay, and let's go ahead and look. What can you tell me about the motion of this armadillo and why? Well, it looks like it's not moving because, and the why I'm going to give you is that the position stays the same as time passes. So if its position isn't changing, but time is, then it must not be moving. Okay, it must be standing still. Okay, and then let's look over at this armadillo. It looks like as time passes, the position is changing. Okay, and it looks like potentially the position is changing at different rates. Okay, and so the question I have for you here is during which portion or which part of the graph is the armadillo moving the fastest? Where do you think the armadillo moves the fastest? And why? How do you know? How do you know it moves there the fastest at that point? Well, I'm going to tell you that one way you can look is by looking at the slope. Okay, so the line here starts off, it gets steeper, it gets steeper, it gets steeper, and during this segment here is where it's at its steepest, and then it starts to slow down again. Okay, in these 3 seconds it travels about 5 meters, whereas in this 1 second it's traveling 2 meters. So in this region here it's traveling the fastest. It goes the furthest amount of distance in the shortest amount of time. Okay, and so that would indicate to us where it's going the fastest. Okay, so we'll say armadillo 2 moving a little bit faster than armadillo 1. So now let's talk about actually quantifying the speed of these armadillos. Okay, and when we do that, we can talk about two different things. Okay, we can talk about the average speed, and actually instead of speed we're going to use a different word called velocity. Okay, and I'll explain the difference in a second. We can talk about average velocity. Okay, or we can talk about instantaneous velocity. Okay, and these are two different things. Okay, and the distinction is important. It's something that we really need to understand. Okay, if let's say that I traveled, so like this summer I went to visit my family that lives in Northern California, and that drive normally takes me about 6 or 7 hours. I was traveling with my kids, and because of that, there were several reasons why we had to stop multiple times, and instead it took me probably 8 or 9 hours. Okay, and so if it's about 400 miles, let's say it's 450 miles. Well, if it's 450 miles and it took me about 9 hours, then my average velocity, the average rate that I was traveling, would be 50 miles per hour. Okay? Now, Instantaneous velocity, on the other hand, is referring to the velocity at any point along the drive. Okay, so probably the fastest I traveled while I was driving was 80 miles per hour, and at that instant my velocity would have been 80. There was other times where I was stopped, and so at that time my velocity would have been 0. Okay, and so this is kind of highlighting some of these differences between average and instantaneous velocity, and so we're going to be talking about that in the next couple segments. But looking at this armadillo here, what could we say its average velocity is from 0 to 4 seconds? Sorry, that's a S, not a Z. Okay, well, the way we would do that is we would find the change in position during that time. It looks like it doesn't change, and we could divide that by the total time. In this case was 4 seconds, so it has an average velocity of 0. And the next question I have for you, of armadillo number 1, what was the instantaneous velocity at 3 seconds? Well, the way that we would kind of find this is look at the slope of it, how the position is changing. Since it's not, we could just say, okay, that's going to be 0 meters per second. Okay, so in this case, the average and instantaneous velocity were the same. Alright, but one indicator that we can use when we're talking about velocity, if we're looking between two times, that's a clue that we're finding average velocity. If we're looking at a single time, that's a clue that we're finding instantaneous velocity. So as we mentioned, we can get velocity by finding the slope of a graph. Okay, and so average velocity can be found by finding the slope between 2 points on the graph. Okay, so if we wanted to find the average velocity of the second armadillo from 0 seconds to 4 seconds, we could connect them with a point, with a line, and find the slope of that line. Now, as you can see, that line doesn't really represent the slope of any particular point, except for maybe a couple points, but what it kind of gives you an indication of kind of the average trend of the motion of it. Okay, because it's fluctuating a little bit. It went slow, it went fast, and you could think of it another way, where if something was going at this constant speed, it would arrive at the same location at the same time. Okay, so the average velocity would be the change in position there. So we went up 1, 2, 3, 4, 5, 6, 7 meters, and it took us 4 seconds. Okay, so 7 meters in 4 seconds tells us the average velocity of that armadillo is equal to 1.75 meters per second. Okay, so the way that we calculate the slope or the average velocity is by finding the displacement of an object and dividing it by the total time that's passed. This is how we calculate average velocity. And average velocity is a vector. Okay, what does it mean that it's a vector? Okay, meaning it has magnitude, how much, and direction. So if we were going in the positive direction here, that this is a positive average velocity. Okay, and so if we're saying that positive is to the right and negative is to the left, then for us to have a positive velocity, that tells us we're moving to the right, and then when it's negative, we're moving to the left. Okay, we can also talk about speed, and speed is the scalar version of velocity. Okay, and there's a big difference here. When we calculate speed, we're taking, instead of the displacement, we're taking the total distance. Okay, and so something to think about. When we do calculations with a vector, we get another vector. Okay, when we do calculations that don't involve vectors, where all the values are scalars, distance is a scalar, time is a scalar, we end up with another scalar. Okay, so speed would be the scalar version of velocity. In this case, the average speed and average velocity would be the same. Okay, Okay, so here we have a scenario where we're driving a pickup truck that travels a certain distance at a certain rate, and then it's going to run out of gas and stop. And then over the next 30 minutes, we're going to walk to get gas. Okay, and so this is an opportunity for us to kind of explore some of the ways we can use the formula for average velocity. Okay, an average velocity, remember, is equal, and we'll use the bar above it. This bar shows average is displacement divided by time. And one of the things that we can do in physics is manipulate these equations. So it says, what's the overall displacement from the beginning of your drive to the arrival at the station? Okay, well, I'm going to let you answer that. So overall displacement, we traveled 6 kilometers, and then we stopped and we traveled 2 kilometers more. Okay, so in this case, where we know that displacement is final minus initial position, in this case, we're not given positions, but actual displacements, right? So 6 kilometers gives us a change in position, and 2 kilometers gives us an additional change in position. So we wouldn't quite use this calculation here because these are not positions but changes in position. So we can actually just add them together, getting a total displacement of 8 kilometers. Okay, then it asks for the time interval from the beginning of your drive to the arrival at the station. Okay, well, it says that we walked for 30 minutes. Okay, so we went, we'll say it's 0.5 hours. Okay, well, we also have to figure out how long we drove at this part. Okay, so how long were we driving during that first interval? Go ahead and figure that out. So this is an opportunity that we can use this equation, we can manipulate it. If we know that our average velocity was 60 kilometers per hour, we can replace v with that. We know that our displacement is 6 kilometers, so we can solve this for t. Okay, and so the way that we can do this is we can swap these guys right here to make it t equals 6 over 60, and the hours will go up to the top. Okay, so we're going to end up with 0.1 hours, which a tenth of an hour is just 6 minutes. Okay, but we'll use 0.1 since we're using the 0.5 there. So that's 0.1 hours plus 0.5 hours is 0.6 total hours of travel. Okay, then it asks us to make a displacement time graph. Okay, and we can we'll call it displacement because we'll just say starting point is 0. Alright, so the total time travel is 0.6 hours. So 1, 2, 3, 4, 5, 6. And at this point, at 0.6 hours, we were at the furthest position away of 8 kilometers. Okay, right there. And then working backwards, it took us 0.1 hours to go 6 kilometers. Okay. And so this would be our displacement or position time graph. Okay, during which interval was it going the fastest? This first one, right? The slope is the steepest there. Okay, then you're walking much more slowly. All right, the average velocity of the total trip would be the total to do numerically would be total displacement divided by the total time. Okay, a displacement of 8 kilometers over our total time of 0.6 hours. That gives us an average velocity of 13.3 kilometers per hour. Okay, then it says to create to do it graphically, that'd be to find the slope from here to here. That'd be 8 over 0.6 again. Then create a velocity time graph. Okay, so velocity versus time. For the first 0.1, it was traveling 60 kilometers per hour. Okay, and then from 0.1 to 0.6, we're going at the slower speed, covering 2 kilometers in 30 minutes. Okay, so 2 over 0.5 gives us 4 kilometers per hour. Okay, go ahead and finish this up, and we'll check it tomorrow. Go ahead and do part D right here.